Welcome everybody. Good evening, good afternoon, and good morning. I will welcome to this expert session on photonic wire bonding. And before I switch to photonic wire bonding topic, I would like to focus your attention on two technologies that revolutionized the world of photonic in the recent decades. And the first one is photonic integrated circuits, PICs. And to illustrate the power and the impact of this technology, let's look at this prediction from the YOL study from 2025, prediction of the growth of the global market of PICs in the next 5 years. And it's showing the 9 times increase of the value of the global market exceeding $4 billion in 2030. And you see that every single material platform of the PICs, whether it is silicon on isolator, lithium niobide, indium phosphide, or silicon nitride, every single branch of PICs in production technology will experience more than 20% yearly growth. And regardless of the material, regardless of the platform, there will be a tremendous need for a PIC to word interface, connecting the PICs to the outer world, either to other PICs or to optical fibers. And talking about the fibers, the backbone of global communication, the numbers here are also very impressive. There is, according to some estimation, more than 4 billion kilometers of fibers installed all around the world. And it is equivalent to surrounding the equator 100,000 times. And if you like to play with such a big numbers, so then you can imagine that if you wrap the word 100 times with the fibers one by one, they will build a fiber ribbon which is 25 meter wide. It would be a highway made of optical fibers. So what makes the fibers so special is that they are very well theoretically understood since already since the 60s in the last century. And I will use some pieces of this theory behind the fibers also in this talk. The fibers are pluggable, they have low propagation losses, they are elastic and bendable, which is also one important aspect which I will refer to today. And the fibers are connecting devices, houses, cities, and even continents. But can they also contribute to connecting between a very small objects like PICs? And before I answer this question, I would like to focus your attention to the size mismatch of the fibers and the PICs. Well, the fiber itself is much smaller than a PIC, but the fiber connector is much larger than a typical PIC. And thus, it is very difficult to connect a single fiber to a PIC, at least permanently. And what is usually done is connecting an array of fibers to the surface or to the facet of the PIC, like in this picture. So this topic, connecting fibers to the PIC, have been the topic of my previous expert session on optical fiber coupling to photonic chips. You are welcome to look it on our website or on YouTube. And so the answer is that the fiber arrays can connect the PICs to the world, but what about the inter-PICs connections? So what is meant by inter-PICs connection? We will need to look at the PIC puzzles. In the modern photonic systems, there are the combination of best-in-class technologies is used, because every brick of these puzzles is used to fulfill a specific function. Either it is a light source or a modulator or a photodetector. And these bricks are often made of different materials like silicon nitride, indium phosphide, lithium niobide, or glass. And in the modern systems, also the required this variety of wavelengths ranging from ultraviolet to infrared, and a high integration density together with electronic chips. And a monolithic growth of such a combination is often not possible, or if in some limited cases, if it is possible, the costs are very high. So the answer is to use a chiplet approach with this Lego-like hybrid integration, assembling of all of these individual bricks on a common substrate. The idea is not new, because the chiplet idea is known from electronics. And here you can see an example of electronic chiplet on a glass substrate made at Fraunhofer IZM. But now we want an optical chiplets, and they required low loss interchip and chip to substrate connections, optical connections. They required active or highly precise active or precise passive alignment to the substrate. And they required a substrate which enabling optical routing between the chips, which means that the substrate should have integrated optical waveguides. So here again, these three requirements will be touched in the three upcoming sessions, starting with the sessions of today about photonic wire bonding. So let's define the problem again. So we have a substrate for integrating of PICs. The PICs are placed on the substrate with gaps having tens to hundreds micrometer. And this is usually too low space for connecting the fibers or micro optics. And there is some inaccuracy in placing these PICs due to the mechanical inaccuracy of the die bonder, reaching tens of micrometers, and this leads to some offset of the height of the horizontal position or some rotation, and whereas this offset can be easily compensated for the electronic connection with traditional electronic wire bonds. This offset of a few tens of micrometers is really bad for optical connections. So what we need is equivalent of electronic wire bonds to bridge the optical connections. And these are the optical or photonical wire bonds. So they are tolerant to the misalignment. They support parallel connection of several waveguides. And they, most importantly, they allow for adiabatic transformation of the optical mode for the case that the waveguides to be connected have different size of the optical mode. Now, how can such photonic wire bond be made? In principle, these photonic wire bonds are highly precise 3D printed polymer waveguides. There are different methods for 3D printing, and for photonic wire bonds, the method of use is voxel by voxel photopolymerization in a liquid resin. A voxel is a three-dimensional pixel, and the polymerization happens only above some certain intensity threshold of the laser field. So if you focus the laser, then the polymerization happens only in the vicinity of the focus, and this is the voxel. And how large or how small can such voxel be? For the linear optics, the diffraction limited diameter of the focus for high numerical aperture objectives is roughly about the order of the optical wavelength. So it would be about something under a micrometer. But if the polymerization process is a two-photon process, then the probability of absorbing two photons is proportional to the intensity square, and thus the effective focus diameter is smaller than the diffraction limit, and the corresponding voxel is even smaller. And the typical voxel size is 200 to 300 nanometer in the lateral direction and 500 nanometer in the axial direction. And this allows us to print the waveguides with sub-micrometer cross-section. This is how it may look in the reality. The two peaks are placed on a common substrate. They are positioned on the movable XY table. And there's a little droplet of the photoresist between the peaks. And up there's a high numerical aperture microscope objective with most commonly with immersion oil. And the focus of the laser is moved with a galvo scanner and a f-theta lens. So here's a picture of a real machine, and it has a vision system which automatically recognizes the waveguides with 20 nanometer resolution, and the writing precision, the precision of movement of the focus of the laser is under 50 nanometer, and the working area of this galvo scanner is 350 times 390 nanometers, micrometers. So now let's focus on the basic physics behind the photonic waveguides, photonic wire bonds. In principle, it's a step index cylindrical or elliptical waveguide. And here you see a comparison of a fiber cladding and fiber core. And here for comparison in the right scale, there's a much smaller in diameter photonic wire bond. And nice thing that it's simply a cylindrical waveguide is that we know that theory behind it is well established since the pioneering decades of optical fibers from the 60s and 90s and 70s from the last century. So what can we learn from this basic theory? We can learn about the mode variety, which means the distinction whether the waveguide is single mode or multi-mode. We can calculate the size mode field diameter, the size of the optical field, depending on the radius of the waveguide and on the optical wavelength. We can calculate the bending losses or adiabaticity condition for tapered geometries. Here you see a basic example of realized coupling between two fibers, and this is a coupling from single mode to single mode fiber with telecom wavelengths. They are in distance of 300 micrometers, and you see here on both sides a tapered section, and the actual photonic wire bond is here in the middle. We reached the propagation loss of the insertion loss of 2 dB. This corresponds to transmission of 64%. although I need to mention that we don't know exactly the propagation losses. There are some values from literature saying that it's up to more than 5 dB per millimeter. And we plan some dedicated experiment to measure this propagation losses. Now let's see a basic schematic of fiber to PIC coupling. We have optical fiber, a top view, optical fiber, a tapered section at photonic wire bond, and a PIC with the waveguide. And the waveguide is offset to the optical axis by some few tens of micrometers. And the photonic wire bond is to compensate for this offset. This compensation is only possible if the photonic wire bond is a single mode waveguide. Otherwise, there will be excitation of higher modes and losses. To see whether the waveguide is a single mode or multi-mode, we need to calculate the so-called V parameter, which depends on the size or radius of the waveguide, on the wavelength, and on the difference in the refractive index. And now if we plot V parameter as a function of diameter of the photonic wire bonds, it scales linearly as expected, and the theoretical limit for single mode waveguides is the value of V 2.4. Below 2.4, the waveguide is single mode. Our current operating point is the diameter of 1.7 micrometer, which is fairly enough single mode operation regime. So what about the other wavelengths? For smaller wavelengths, the V parameter should be larger. And indeed it is. If you plot now the V parameter for the other wavelengths, you see that for the given diameter, the V parameter is larger. But if we are able to print the sub-micrometer photonic wire bonds, then we should be able to print single mode waveguides down to wavelength of 530 nanometer. Now, what about the taper? The taper is much thicker than the photonic wire bond. So if we print the V parameter for the taper, for its diameter up to 13 micrometer, you see that the V parameter value lies above 2.4, and clearly the taper is multi-mode, even for the infrared wavelength 1550 nanometer. So the message is that the taper is a multi-mode waveguide, and it has to be straight, otherwise it will lead to unwanted losses. Now the question of adiabaticity, or first of the transformation of the optical field, evolution of the optical field in the taper. So the starting point is the diameter matching the diameter of the optical field in the fiber, and at the end we want to have a mode field diameter typical for a PIC. And here again there's a formula from the paper, from an old paper from 70s. It's approximating formula showing the evolution of the mode field diameter along the taper. It starts with some 9 micrometers, and at the end it's 2 micrometers, which is a typical mode field diameter for a PIC, for a silicon nitride PIC, for instance. And the yellow point is the result of a numerical simulation. And luckily for this numerical simulation, it is in agreement with the nice analytical prediction from the 70s. Now the question of adiabaticity, is it adiabatic transformation? There's again an estimation from the 70s, and the adiabaticity condition says that the taper angle must be smaller than lambda over the radius of the waveguide. And here again is a plot. The orange line is the taper angle. For a linear taper, the angle is constant, and indeed it is for almost everywhere smaller than this adiabaticity condition. Of course, it's approximation formula. In order to calculate the losses in the real waveguide, we again used a numerical calculation. And here you see transmission of a transmission into the fundamental mode and the ground mode of the photonic wire bonds from the taper as a function of the taper length. And as expected, the longer taper is more adiabatic, and the longer taper give us more transmission. Our current wavelength of the taper is 130 micrometers, and it corresponds to a transmission of 82%. And if you now remember the transmission of this system fiber to fiber, it was 64%, and if you square 82%, then you end up at 68%. So it is almost in agreement with the prediction. Now here you see a microscope picture of a real coupling from a fiber array to PIC. You see that there's an almost intentional shift offset of 30 micrometers, and it is bridged with a photonic wire bond. We reached transmission here of 56%. It is 2.5 decibel insertion loss, but you need to know if you couple this fiber array directly to the PIC with the bad coupling, the transmission would be 90%. So the possible issues here is why this transmission is lower than expected is that we don't know exactly the mode field diameter of the PICs, so we would have to scan the taper parameters of this second tapers, adapting the mode field diameter of the photonic wire bonds to that of the PIC. And also you see here a vertical misalignment, but you also see that the focus is the left taper is in focus of the microscope, and the right taper is out of focus, which means that the height also is different. We don't know exactly this height difference, and maybe there's a vertical misalignment in addition to the horizontal misalignment. Now another example, and here I go back to the platform carrying the optical chiplets with optical routing through the waveguides in glass, and we realized coupling of this glass in waveguides to a fiber array. Here's a fiber array with 12 channels, and on the right side there's a glass, again a microscope pictures. In this case, the waveguides in glass are hardly or not at all visible, typical for glass, because this is a very low, these are very low contrast, index contrast waveguides. The transmission we reached is 71% per connection, which is very similar to the fiber to fiber case. Again, if you want to experience more about this platform and about the waveguides, ion exchange waveguides, please visit the third session on 10th of March on glass core substrates. So what are the challenges? The main challenge is to improve the coupling efficiency. We will have to estimate the propagation losses in photonic wire bonds. We will have to perform the parameter scans of the tapered diameter and of its position. And finally, we need to shorten the taper section. So we need to go away from the linear geometry. There are also some theoretical predictions for transformation for adiabatic transformation of the optical field. One of them, again from the 70s, is predicting that the ideal shape would be a parabolic instead of a linear taper. There is also another more fancy approach from the paper, very recent paper from last year, from 2025, and it is using the inverse photonic design to calculate the shape of the not taper, is rather a structure, a fishbone-like structure. It is only 25 micrometer long, and the performance coupling efficiency to the photonic wire bond is very promising. Another challenge is going to the shorter wavelengths. We saw that the printing of photonic wire bonds for single mode photonic wire bonds is possible, but the shorter the wavelengths, the higher assembly precision will be required. And the last challenge is the material research, search for high temperature resistant materials in order to make the photonic wire bonds compatible to the reflow soldering. So many thanks for your attention. Thank you very much. And I'm open for questions, and contact me if you have questions, also per email.